With this video, I'm going to summarize the reactions of the module. Now, when I refer to whether a reaction follows Markovnikov or is anti-Markovnikov, what I mean is if it's Markovnikov, that means the electrophile is going to be added to the least substituted carbon. Oftentimes that means the hydrogens are going to play together. So where there are more hydrogens, a hydrogen will bond, or the electrophile will bond there. Nucleophiles will bond or attach to a more substituted carbon. So that's what I mean when I say we are following Markovnikov or we're going anti-Markovnikov. Now I'm going to complete all of these reactions with the same molecule in order to show you the differences. So we're going to use a 1-butene. Now the first reaction we're going to do is called hydrohalogenation. This is where we have an HX, and that X is going to be either chlorine, bromine, or iodine. Now, hydrohalogenation can add both syn and anti. That means the same side or opposite sides of that pi bond. It does go through a cation step, so watch for rearrangement. Now, that rearrangement can be a cation rearrangement. It could be, so that would be a hydrogen shift, or you might want to watch for that methyl shift as well. This is a Markovnikov reaction. That means the hydrogen or the electrophile will be bonded to the carbon that is least substituted. So here's my least substituted carbon. And then in a different color, I'm going to come over here and do my most substituted. You see my least substituted, this has two H's. My most substituted, that's this carbon. This carbon has one H and it also has one carbon. So that's more substituted. So because hydrohalogenation acts both syn and anti and in the Markovnikov fashion, then we have the H bonding here. So we have a methyl group on this side, and then we have our X to the more substituted carbon. Then we have hydration. Hydration is when we add water with an acid. It's a strong acid. We usually use sulfuric acid. Now, hydration, we have both syn and anti. There is rearrangement, so watch for that rearrangement because it does go through that cation step. And this is a Markovnikov addition. So just like the hydrohalogenation above, in hydration, we have our nucleophile, which in this case is the OH, going to the more substituted carbon. We've added an H here, so this side is now a methyl group. We don't oftentimes draw those little H's in. We oftentimes just leave them off so that we have a carbon at our end and our bend. So let's just clean that up and be consistent. Then we have halogenation. Halogenation is where we have a diatomic halogen. So we have elemental halogen. Now in this case, the halogen will be chlorine or it will be bromine. When we have this, what we end up forming is called the vicinal dihalide. And that's where we add our halogen to both the more substituted and the less substituted, just directly across that pi bond. This can go anti only. This one is anti only. There is no rearrangement, and we don't worry about Markovnikov or not because we have an X adding to both sides. That's called halogenation. Then we have a halohydrin formation. Halohydrin is where we have our halogen, our diatomic halogen, but this time we add water. Now the X can be chlorine or bromine, just like above, but we've added water. That's an important step because rather than making this vicinal dihalide that we made in the halogenation reaction, the X only goes to the non-substituted or less substituted carbon. And the OH then goes to the more substituted carbon. And that's because, remember the mechanism of this one, the pi bond actually ends up creating a polarity between our X2. So we create this electrophilic halogen. Creating that electrophilic halogen ends up attaching that attaching that electrophilic halogen to the less substituted carbon, and then the nucleophile, or the OH, to the more substituted carbon. So this is Markovnikov, but you have to understand which is your electrophile and which is your nucleophile. This is also anti-only. There is no rearrangement, and that is halohydrin formation. Then we have hydroboration oxidation. Hydroboration oxidation is where we have two steps. So we have our boron trihydride, and then we follow it with some peroxide and a base. And when we do that, we form the primary alcohol. This is anti-Markovnikov, and it is an anti-addition only. This is hydroboration oxidation. It is anti-addition only, and there is no rearrangement. So there's no rearrangement to worry about. Because this is anti-Markovnikov, the hydrogen ends up going to the more substituted carbon, where the OH ends up on the less substituted carbon. So depending on the reagents that we use, we can make 1-butene an alkyl halide. We can make it a secondary alcohol. We can put a vicinal dihalide, so 2 halogens on it. We can make it a halogenated alcohol, secondary alcohol, or we could make it a primary alcohol. So those are the general reactions for our pi bond. Well, what about our triple bond? Well, if we take, and I understand that the geometry here is incorrect, but we're going to take 1-butyne, and I'm going to start, let's see, I started with hydrohalogenation above. So I'll start with hydrohalogenation here. So with hydrohalogenation of an alkyne, you need 2 equivalents of HX. And that X is either going to be chlorine, bromine, or iodine. When you have those 2 equivalents, you're breaking both pi bonds. So you get X's in here on the more substituted carbon, and you get H's on the less substituted carbon. This is Markovnikov. You do have to check for rearrangement. And this is both syn and anti. You see, we're adding 2 H's and 2 X's, so it kind of all plays out that way anyway. Then, let's see, we did hydration next above, so let's do hydration here. Hydration is the addition of water with sulfuric acid. With an alkyne, however, you tend to need this mercury sulfate as well. Now, with the hydration of an alkyne, you end up forming a ketone. So the new bonds here, let's switch my colors real quick. The new bonds, you end up with 2 hydrogens here that weren't here before. There's 1 hydrogen out here. And you end up with this double bond to oxygen. This is also new. So hydration of an alkyne forms a ketone. Let's see, then I think we did halogenation. So let's do halogenation. Halogenation of an alkyne, we need 2 equivalents, and those X's can be chlorine or bromine. When we have those 2 equivalents, everywhere we had an sp2 carbon, we now have 2 X's. This is called, I made it an H, 2 X's. This is called halogenation. And then we can do hydroboration oxidation with an alkyne as well. I'm going to run out of room. But we need this alkyl borohydride. We'll follow it with hydrogen peroxide and a base. And we end up forming, this is where we get our aldehydes. So when we have a triple bond, we can form this geminal dihalide. That's where we have halogens on the same carbon. You can form a ketone with hydration, so you have water and a strong acid. You can form 2 geminal halides, so you end up putting 4 halogens across those pi bonds with halogenation. And then with hydroboration oxidation, from a triple bond, you would form an aldehyde.